binomial theorem for any positive integer n and some special cases. In this module, you will learn about the binomial theorem for any positive integer n and some special cases. The binomial theorem for any positive integer n is given by. To prove this theorem, we will apply the principle of mathematical induction. So, let the given statement be: for n is equal to 1, we have p of 1 is equal to a plus b whole raised to 1, which is equal to 1c0a 1 plus 1c1b1, and this is equal to a plus b. Thus, p of 1 is true. Let p of k is true for some positive integer k. Therefore, we have, name it equation 1. Let us now prove that p of k plus 1 is also true. So we can write a plus b whole raised to k plus 1 as a plus b into a plus b whole raised to k. From equation 1, we know that a plus b whole raised to k is equal to. Therefore, a plus b whole raised to k plus 1 is equal to. By actual multiplication, we get. On grouping like terms, we get. Now, by using the following results, we get. Thus, p of k plus 1 is true whenever p of k is true. Therefore, by the principle of mathematical induction, p of n is true for every positive integer n. Hence, for any positive integer n, we have. This can be written as sigma nck into a raised to n minus k into b raised to k, where k is from 0 to n. Let us now consider the following important observations about the binomial theorem. Coefficients n, c, r in the binomial theorem are called binomial coefficients. The number of terms in the expansion of a plus b whole raised to n is n plus 1, that is, more than the index. It is clear from this expression that the index of a goes on decreasing by unity in the successive terms. Here n is in the first term, then n minus 1 in the second term, and so on, and 0 in the last term. Similarly, the index of b increases by unity. Here 0 is in the first term, 1 in the second, and so on, ending with n in the last term. We can also observe that the sum of the indices of a and b in the first term is n plus 0 equal to n, n minus 1 plus 1 equal to n in the second term, and so on, ending with 0 plus n equal to n in the last term. Let us expand x plus 5 whole raised to 4 to understand this theorem better. On expanding it by using the binomial theorem, we get x plus 5 whole raised to 4 is equal to x raised to 4 plus 20x cube plus 150x square plus 500x plus 625. Let us now consider some special cases. Case 1. In the expansion of a plus b whole raised to n, if we take a as x and b as minus y, we get x minus y whole raised to n, which is equal to x plus within brackets minus y whole raised to n. Now on expanding it, we get Therefore, x minus y whole raised to n is equal to Case 2. On taking a equal to 1 and b equal to x, we get 1 plus x whole raised to n, which is equal to in particular, if x is equal to 1, then 2 raised to n is equal to nc0 plus nc1 plus nc2 plus so on plus ncn. Case 3. On taking a as 1 and b as minus x, we get in particular, if x is equal to 1, we have 0 is equal to nc0 minus nc1 plus nc2 minus up to minus 1 raised to n into ncn. In this module, you have learnt about the binomial theorem for any positive integer n and some special cases.